Okay, I think we might be ready to go. We might be ready to go. Let me know in the chat if you can hear me all right. 1, 2, 1, 2. As usual, I'm just crashing into this one, totally prepared. Ow. Hey, you can hear me? Good. Glad you can hear me. Good. That's good to see. Right. Yes. Okay. Wednesday nights are a bit tight for me. I have other things to do, which meant I got home at about 7, had to stuff some tea in my face, and then get over here to get this happening. So I think I've pulled it together. I think I have everything in the right place, and I should begin, of course, by saying welcome. You're very welcome. This evening, this is a live stream on my series of Erica Synths DIY educational builds. The educational bit is that we learn together. So I'm not here to teach you anything. I'm here to learn from the documentation, from the resources and the materials provided by Erica Synths, and of course Moritz Klein, who's written it all. And we're going to learn from it together, hopefully build a module on a breadboard and look at it, examine it, get it to work out what the heck's going on with it. I'm going to need some other bits for this, aren't I? Oh, we'll work that out when we get to it. So that's the plan. That is the plan. So tonight, we are working on the envelope generator. Now, ideally, if you're playing along at home, you should have 2 of these. The reason being, you have one for the VCA and one for the filter. Or, I mean, it's a dual VCA. You can have both for the VCA if you like. Do what you like with them. They're envelopes. You can envelope anything you like. Don't fall into the trap of thinking you can only envelope one sort of thing. Envelope whatever you like. It's very exciting. So that's what we're going to build. I don't know how complex it is. Looks really easy on the box, but obviously I'm not going to build 2. That would be ridiculous. I'm going to build 1, and we'll see how that goes. And what I hope is going to happen during this evening is that we are going to together learn how an envelope circuit is put together. Learn about envelopes, of course, as well at the same time. Yes, possibly, but the focus of these videos, this series of videos, is the electronics. And so that's what we're focusing on. So I'm not going to spend any more time talking about it. I think we should just get on with it. I've got the manual up on my screen here, which I'll also throw up onto the screen so you can see it at times, depending on what we're doing. And hopefully we'll be able to all see all what's going on all at the same time and not get confused or troubled by anything. It will just be smooth and lovely. That's the plan. So let's have a look at the bits in the box. Now, if you just excuse me, I've got to work out which thing does the right thing. There we go. That's the top down. Look at that. So here's what we're going to get to. Probably not tonight. Probably tomorrow night. I have tomorrow night penciled in as well, because my assumption is that I'm not going to be able to do the breadboarding, the learning, and the soldering of the kit all in one session. It hasn't worked out like that. You know, when I first started this, I thought, yeah, a couple of hours, whole lot, no problem. No, a couple of hours and we just about get in to the breadboarding. So, you know, sit back, make yourself a coffee. Oh, I wish I'd done that. Anyway, so here's the front panel of the envelope. Looks like we've got a gate. It has some looping, attack, decay, release, sustain at the bottom. So it's slightly different in that it has decay and release together, which speaks to me actually, because I tend to find that an ADSR is a load of stuff that I don't necessarily use, and I tend to use or prefer an ASR really. Just attack and then hold on to it and then let it go. I'm not really feeling the need for that sustain level, where's that going to be? That down and then adjust, you know. But that's just me. I like to keep things simple. So that's that. This is the PCB, which does not look difficult. See, this looks like it's going to be relatively straightforward. Yeah, nice. Put those to one side for the moment. In here, we've got the hardware. So that's the pots and jack sockets, power cable. And in this one, we have all the other stuff. I'm not going to tip them out yet until it tells me to in the manual as we start to put this onto the breadboard, or we go through the bill of materials. Yeah, see, that's an idea. Let's do that, because that's what they have now. After that's what we were able to achieve between us, is that when we did the first one, the lack of a bill of materials was a little bit of a problem. And so ever since, there have been bills of materials, because this is, if you like, an evolving project, and that things that we find in doing this, if we trip over some stuff, if we find some weirdness, then hopefully that can be improved for future builders. That's part of what we're here for. So let's have a look at the manual and have a go. I'm just checking to see whether this is important. Okay, good. No, we're going to just get straight to the business about the envelope. You can download this from the Erica Synths website, from the shop page, and also there's a link in the description of this video to go and check that out. Everything's still working out there in TV land? Let's hope so. Okay, so we need to look at the manual. 1 second. Is that this one? Yeah, okay. So I just need to keep it over smaller a little bit. So this may feel like I'm just reading through it, which is because I kind of am. that's the way we're going to be learning things, all right? But I will try my best to keep it snappy and to just go through this as firmly as we can. So let's get started. Everyone ready? Don't need your soldering iron today, not yet at least. We'll just be looking at hopefully a breadboard, which is this fella. Okay, we're going to get to that in a minute, and we'll work out why it's weird and strange and different and awesome. Good. Right, envelope generators. These are one of the most important sources of control voltage in any modular synthesizer. They don't generate audio signals, but many arconic sounds. Okay, we know all about that. So this is why we needed one, and we created this wily little fake ADSR. Ooh, why fake, he says? Well, because it doesn't send out a 4-staged signal: attack, decay, sustain, release. No. The duration of the decay and release are tied together, controllable only via the same knob. How weird. To make up for this limitation, I've decided to include both a looping function and an inverted output as extra goodies. See, I would argue that not having a full ADSR is no problem. Absolutely no problem. I don't think sustain is used a whole lot, personally, in modular. You know, it's good for big evolving pads where you want this big sort of mountain and then a relaxed thing and then a release. Yeah, I can get that, but at least my experience in modular, I just want rise and fall, you know, quick bam 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 type stuff. I think. Or if I want something long and evolving, I'll tend to use an LFO. But I don't want to digress into that. We want to get straight on with what this is telling us. So here is our circuit diagram. So we have some kind of gate input. I can use my pointer thing for this because then it will appear on your screen. You've got a gate input. There's a capacitor there, some diode stuff going on. Look, there's a resistor going to ground. I can't remember the name of that now, but that's something. Then these op amps. See, I'm remembering all this stuff from previous. Another diode. There's 2 sides to this. Some kind of variable thing in between. There's another 100k going down to another variable thing here to ground. Then there's a loop switch which goes in as another op amp. Then there's some strange array of diodes here with 1 meg resistors. Interesting. Then a capacitor going to ground. Ooh. Then that's an output. Meanwhile, down here, there's a status LED, some kind of other wizardry, and then a backwards thing. So I think we've aced it. I think we know what we're talking about. Yeah. Anyway, so bit of materials, great. So we have an opportunity to have a look through our stuff so that we know what it is. That's always going to be good. So let's get these things out on the table. And let's go back to our previous one. Okay, good. Smooth as silk this is, smooth as silk. One of these days I'm going to work out having a preview monitor rather than behind me, somehow in front of me. But I've already got 2 laptops, Surface things I'm using for things, so heck, can't have it all. Right, so resistor town, let's start off with that. Get everything else out of the way. Resistors. Got a colourful bunch today. One of those. Let's move everything else just out of the way for a second. So we should have 10 100k. Now I've only got this lot, which are 10, so it must be them. Now, do I have a pen? Pen. Usually have a pen. That'll do. A pen this week is provided by Arturia. Your experience, your sound. Okay, so these are 100k. Without a doubt. I don't have to measure them. You could measure them, or you could look at the bands and then look those up and know what they are. But we know what they are because there's 10 of them. It's the only group that's got 10. If they're wrong, it's not my fault. Somebody else's fault. Now, the rest are going to be slightly more interchangeable, so we might have to test these to work these ones out. So we have 147. So I'm going to get my meter, stick that into shot somewhere. I've lost my crinkly ends. Where have my crocodile ends gone? There's one, there's another. Okay. Put it across to ohmage. Here's one. Now I'm going to predict that this is, I can't see the bands, my eyesight's not good enough. I'm going to say this is a 10. Can I get it to go? Look at that, 10k. Told you, because it's blue, right? So is there one 10k? Yes, there is. So that's a 10k. Good, put that to one side. The next single. Come on. That's 100 ohms. Is there 100 ohms? Yes, there is. That's 100. Next one is here. Okay, so that's 0.47k. So that will be 470 ohms. So I'm not doing it on camera, am I? So this is 470. So this last one should be the 47k. 47k, got that? Well, yeah, 46.8, close enough. 47, that was terrible writing. 47, 47k. Now I've left with 2 lots of 2, so I should get 2 1k and 2 10 ohm. right, just about 10 ohm. That's 10. And this final one should be 1K. Yeah, 1K. Good, that's all the resistors tested. Lovely. So what's next? A few capacitors, it says. So we should have some electrolytic, 47, they're usually written on, so that's not difficult to find. 47 microfarads, 2 of those. Electrolytic are the big fat ones which have the different length legs to tell us which is positive and which is negative. There's a film ones, which will be these 2 white ones that don't have anything helpful written on them at all, but just through process of elimination we know what they're going to be, times 2. Yeah. And then ceramic are these little blip ones, these ones, times 8. They usually got 104 written on them somewhere. Yes. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, rock and roll. Some diodes. Specific names are printed on them. But again, if there's 2, that's going to be these fatter ones. And the 6 are going to be these smaller ones. 1, 2, 3, 4, 5, 6. So that's good. These are all being very well identified. I'm liking it a lot. A transistor. This fella, 3 legs, transistor. Specific name will be on the body, but it was only the one, so it can only be this one. This is what I like about simple circuits. I think we might get through this in decent time today. Okay, pots. Pots are in the other bit. Let's empty that out then. So there's 2 of one sort and 1 of another. Are they possible to identify? Oh yeah, look, it says A100K on that side. That says 1M. And that says 1M. So 2 1Ms and 1 100K. Check, check, check. Good. A switch. Clickety click. Yeah, that seems to work. Thanks, Matt. Yes, 104 obviously equals 100 nanofarads. I mean, that's plain to see for any idiot. Hey, U3 Dark over on Twitch. Very, very welcome. Oh, I should point out, by the way, that I'm also streaming on Twitter. I mean, would you believe it? I can't quite believe it, but I'm streaming everywhere. Streaming everywhere. Everyone is equally, is equally possible to accidentally bump into this live stream on all sorts of different platforms. But Twitch is something that, is potentially interesting. It's potentially a large audience, but can I get any of them to come? No. It does seem to be all about YouTube, at least because that's, I guess, where my largest subscription and largest group of people tend to hang out. So my kind of experiment with restreaming onto multiple platforms is kind of interesting, and I'll keep going, as I think I've paid for a year's worth of restreaming. So I'll continue to try that out. But ultimately, I think YouTube seems to be the place where it works the best for me. But we'll see. Who knows? We might build up a following. So are you 3 Dark? Go and get all your friends and come along and have a little party. Okay. Don't give me discrepancies already. No, the 104 is 100 nanofarads. Or is it 0.1 microfarads? Oh no, see, you're just messing with me now. Don't mess with me. So, LED, got one of those and it's red. Good. Bunch of jack sockets. Yeah, bunch of jack sockets. Bunch of nuts. Too many nuts. No, yeah. No, okay, one for that. 1, 2, 3, 4, possibly. Switched mono black. Yeah. Couple of chips. Here we are, a little bank of chips on here. I've got 3 chip holders and 3 chips. They're all dual op amps. We saw the op amps in the circuit diagram. So, so that's good. You also find a few sockets that are only relevant when assembling the module in the end. Sockets, yes. Gotcha. Good. So before we start, so this is all going to go onto a breadboard, so I don't need those bits. We'll need bits as we go. And this is our breadboard. You can pick these up off anywhere, off Amazon, something like that, for a tenner. And it's upon this that we build our circuit. Now the first thing we have to do is to power it, where we use a pair of 9-volt batteries, these fellas here. And this has caused endless fun and amusement over the course of building these things. So what I did is I made up a little cable in order to make them go in better, using these wire patch cables on the end of a battery thing. So that goes on said battery, and I should have another one of those for 2 batteries, and this allows us to kind of fake the idea of plus and minus 12 volts, kinda, I think, something like that. But let's see what it says. So what you need to do is connect them like the diagram. Can you see the diagram there? Yeah, good. Where you have... Now, my breadboard is actually labelled differently to the breadboard. Or is it? Is the question. See, it depends on which way up you have it. I've tended to have it this way up because the numbers then go in sequence this way, but the numbers are actually irrelevant. But they are useful because when you're starting to put the breadboard together, if I can get a picture of that, just skip ahead a moment. It's useful to be able to see those numbers that are on the manual and roughly put it in the same place. But if I do that, my positive and negative here is actually upside down when compared to what's on screen. Now, is that important? No, not really. If we ignore the positive and negative bits there, that's actually probably going to help us out, because it isn't positive and negative anyway. You've got, you do have a positive, but then you've got 2 grounds and a negative. So whatever you do, it's not going to be quite right, if you follow me. So I'm finding it helpful to have the numbers go this way, the same as they do on there, even if it means that my positive and negative here are upside down compared to what's on the manual. Are you with me? Are you with me? So that, I think, is what I'm going to continue to do, which is what I did at the beginning. So all that's important in terms of the battery is that you ignore the plus and minus bit that's actually written on the breadboard, and you plug in the batteries where it's appropriate and know what it is that is. That makes sense? Right, so all I'm saying is a negative of 1 battery, there's a black and 1 battery, goes to the bottom. Then then think you idiot. Then you have ground, which is positive of 1 side, which goes in there, and the negative of the other battery, which goes in alongside it. You seeing this? And then we have the positive. Now mine is the right way up. Oh, I'm back to front and upside down. Oh, it's just a second. Come on. Come on, you can do this. I talked a whole load of stuff and then completely did the opposite. So negative of this battery goes to the bottom. The positive of that battery goes to the one above it, alongside the negative of the other battery, and the positive goes there on the inside track. You then need a cable to connect this ground to that far one there. I think that's right. So our negative rail is along here at the bottom. We've then got a ground. We've then got our positive rail, and then we've got a ground above the top. Now this, even though my pluses and minuses are backwards, as I say, is what mirrors what's on the manual, and that's what I'm going for. And I like the numbers going up this way, which also matches what's in the manual and allows me to place my components more accurately and better. Does that make sense? That's just a decision I've had to make because mine is labelled differently to the manual one. I think I've labelled that enough. Maybe. Right, so that is the batteries done. Now it says it's a bit awkward or strange because it's not really how breadboards are commonly used, which is true, but we have to have this positive and negative thing because we're dealing with Eurorack, which deals with those sorts of voltages. So we're now on to envelope basics. If you're new to modular synths or synths, you might ask, what's an envelope? Do you really want to go into what's an envelope? Possibly, but essentially it controls voltage over time. So it's like a robot hand helping us out. So we have to understand what an envelope does exactly. How does it tweak parameters on another module? Well, when designing oscillators, filters, amplifiers, you'll notice that people go to great lengths in order to make them voltage controllable. This comes in handy because if we want a filter module to open up, for example, we can simply send a high level voltage into its control voltage input. Now, if you only want it to open If we only want it to open and stay open, we could just send it a fixed 12 volt signal and be done with it, but that's not useful. Usually we want the filter to close, and we might actually want it to move and change over time, which is more common. So the simplest envelope. Since a square wave is really just an oscillation between a high and low level, this could indeed cause our filter to open up and close down again. Even better, it would do so rhythmically as the oscillator cycles through its phases. While this does work, it has two severe limitations. First, opening and closing movements are always instant. There's no way of making them more gradual. This might be what you want, but often you want something less abrupt. You want an attack, a slow opening, or a release, which is a slow closing. We can't change the rhythmic pattern. We also get a constant, all we get is a constant staccato with a square wave. So what can we do about that? Well, the most obvious thing is to try to make the rising and falling edges less steep. In envelope terms, we say we want to slow down the attack and extend the release. Might sound complicated, but it's anything but. Now, you could obviously use a triangle wave rather than a square wave, and that would give you that slant and slope. But what we're trying to demonstrate here, what Moritz is trying to show us, is how we take a square wave and start to make changes to the rising and falling edges, which are going to give us our envelope. So here we go. This is how it's going to work. You're going to have a square wave going in. That's then going to go through a resistor. It's going to have a capacitor pulling charge off so that it doesn't, I'm not explaining this very well, but that's because I need to read the text rather than try to make stuff up. But that, yeah, we can see through our experience now of using resistors that that's going to affect a change, and the capacitor is going to slow that change down. That's my understanding. Now let's read. So all we need is two components, a resistor and a capacitor. Now, if you've worked with analog filters before, it will look strikingly familiar. Well, good, because it's been a little while. It's been a month or two before we really looked at this. Well, it was last month we looked at the VCA, but we haven't actually built any filters. So this is interesting. So well, that's because this is really just a bog standard passive low pass filter. Is it? Now, as I say, this is lost on us because we haven't built the filter. What it does to our square wave is exactly what we said we're after. It takes the rising and falling edges and makes them less steep. Here's how it works. Once the voltage on the input switches from low to high, the current will be forced through the resistor, right, and into the capacitor, slowly filling it up. As the capacitor is being charged, the voltage at the output slowly rises until the cap is completely filled. That's right, because the current is being diverted to ground through the capacitor. But as the capacitor fills up, the pressure increases behind it, which increases the voltage. That's the way we've been looking at it, I'm pretty sure. Are you all right out there? The chat is not quite as lively as it normally is, and that worries me slightly. But anyway, moving on. I'll just keep on going regardless. Then when the input voltage swings low, the whole process reverses. Now the capacitor will push its contents through the resistor into the input, so to speak. This happens because the voltage on the right is much higher than the voltage on the left. As the capacitor empties out slowly, the two voltages align again, and as you can see, this will turn our square wave input into something like a very basic attack release envelope. Before we try this, we're going to try this. We'll have to think about appropriate values for the capacitor and resistor. Since we are dealing with very, very slow square wave oscillation at the input, they'll need to be pretty big, otherwise the effect will be so minimal we won't notice. We'll probably want to adjust the effect's intensity. For that, we've essentially got two options. We could change either the capacitor or the resistor value, but since the former can only be done by hand and switching components is not the most user-friendly strategy, we're going to replace the fixed resistor with a pot. Set it up as a variable resistor. How exciting! This way we can adjust the resistance and therefore the steepness of the edges. This should give us a decent enough range. Excellent. So I'm going to have to find some stuff and turn some stuff on, which I didn't get a chance to do beforehand. But let's worry about that in a moment and just let's get our little circuit built. Neil, thank you for paying attention. Ken, you're not talking because you're too busy doing something else. Okay, I understand. That's fine. I just appreciate you being here. So we've got our little what's it here? That's good. Ready to go? Is that in the center of the screen? Yeah, good. Right. So what it's asking us to do is to plug in an LFO into the input and then do something clever with the output. So we're going to follow what it's saying on the breadboard. So at the moment we need an input, which is the jack. So I'm going to put this over here on 11. I told you, see, those numbers were useful. Put that down like that. Now on the instructions you've just got these patch wires which come hopefully with your breadboard and allow you to patch that to where it needs to go. So that goes to ground. Then we've got this, what have we got? We've got the one micro capacitor. Let's go back up to our bill of materials. Whoop. Capacitors. 1 micro is the film one, square one. Okay, good. Whoop. So this is our capacitor. It goes in somewhere there. And we've got one leg of that capacitor going down to ground. How is this? Is that at either side? Yeah, okay. One leg going down to ground. I've got another leg going to part of the input. So our capacitor is going to ground, but also obviously having to take a signal from the input, which goes there. And then we've got our pot. Which pot? A 1 meg pot. Okay. 1 meg pot. Now these are tricky to put in here. So what I find is that I sort of bend these out, and then that gives me a sideways pot like this. You see, that seems to work the best. And this has to sit in line with this part of the capacitor, like so. Has that gone in? Good enough. 1, 2, 3. Now the middle leg has a cable that comes off it. Can't see. Where is that? There. Middle leg is there. Where's that gone? Gone all skew whiff. No, that's right. Middle leg to there. This comes out a little bit. Then we've got another jack socket where the back leg follows in with that orange cable. Like that. And this end part of it must go to ground. Is that ground? That's ground. Good. So there we go. That's fantastic. There's a little circuit. Now we've no idea whether it's working or not without putting something in and then having to have something that it's going to affect. So at this point, what we need is an LFO and a filter. Yeah, watching machine. Is it a mail order kit? Yes, get it from Erica Synths, ericasynths.lv. Go to the shop and you will find the whole range, well, of what's available so far. What we have so far is a VCO, the VCA, this is the envelope, and also the case and power supply. They're releasing a new one every month, pretty much, and we're working our way through it. Now I just need to go and find a suitably powered LFO and filter. Bum, bum, bum. What am I going to do? Bear with me. Just bear with me. Why not? That's not a thing. That's not a thing. But then if I need a I need an LFO and a filter, I'll need something to go through it as well. So I kind of need a whole synth voice. So what I could do, I mean, it makes sense to use the Erica Synth stuff that I've already got. Hang on. So this is here. I've got a VCO and I've got a VCA. If I could just plug a quick filter into here, simply, that would work, wouldn't it? Yeah, let's do that. Let's do that. Right, I'm just going to try not to break anything over here. Oh, do I have one down here? Right, okay, here's a simple solution. So what I've got here is a Freaks Essential product, which is an entire synthesizer type thing. I could use this, I think, to demonstrate. Does it have an LFO? LFO rate. Sort of. Hang on, bear with me. That's got an envelope. I think that's just making things too difficult for myself. Yeah, it's making things too tricky. Hang on. Right, stand by. Okay, right, so here's a filter. Now is this going to give me... No, I still need an LFO really. Alright. What happened? What happened? Oh. See, I'm looking for my black modulator. It should be right here, and I cannot spot it. Wavetable. Come on, times are going. Well, I never did. What happened to that? What happened to that? Do I have that plugged into something else? Oh, hang on. See, there's modular all over the place. There it is, black modulator. I could almost use now. Right. So this is a black modulator which has a pulse output. Good, that's a relief. Now this doesn't have lots of holes in the right place, so I'm just going to hold it in with a couple. And then this is a filter. Now of course the question is going to be, do I still have the power supply to hand? Are they going to fit there? I'll put this over here. There's a little bit more room, there's not room there. There. Sorry, I would have had this little things prepared earlier. I just unfortunately did not have the time. What do you think shorting the battery? Okay. Right, so we'll come back to the battery thing in a minute. You believe it's shorting out? That's interesting. But quite possibly, who knows? So I need to find the power supply for this. That's that bit. I think it's this. Pretty sure it's this. Yeah, I've got a light I've got a light. So the final bit of the puzzle is going to be to get some sound out. Ba, 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 sound. How am I going to do that? I'm going to need some long cables. So let me think. I've just unplugged that, so that's not going to work. Bring this over here. Those are suspiciously short cables. So is that. Here's a long one. So I need an input. Almost took the camera out. Out, in, out, out, out. Let's take the out the bottom so we're not going across each other quite so much. Okay, still working on it. So we need some cables to go. Let's just take a pulse output, plug it in here. See if we get any sound. Nothing so far. That's an input. That's volume, that should be up. Ugh. Well, that sounds like it should have something. Did I turn it off again? I think I did. That'll be it. Okay, good. Let's turn that off again for a minute. Or maybe it blew up. Did it blow up? No, okay, that's on. Why did I turn it off? Does anybody know what's going on? Okay, there's something. Okay, super. So that's a little bit of output. Neil, thank you. I don't think the batteries are hooked up wrong either. It is still strange how Erica expects us to have an LFO, VCO and VCF without providing those in the set. I agree. But, you know, it's almost impossible to build a modular synth without having a modular synth. You have to start from somewhere, and you can't hear the first thing because you haven't built the second thing, because it all becomes part and parcel of each other. I mean, I think probably having the filter first would have made more sense, maybe. But this is where we are. So, I mean, I'm doing this so perhaps you don't have to. Maybe that's the answer. So, what was I trying to get to? So we need to be able to hear either a filter or something going through. So in which case I just need to patch the... so I got a pulse, yeah. So I need to patch the output of the VCO into my filter so we can hear that in a minute. Signal out from that into there. That's very the clangers at the moment. Good, I can turn that down. So can I arrange this slightly better so it's not all over the place, so I can see what I'm doing? Maybe. Let's bring my breadboard over the side a little bit. I'm going to put this, I haven't got to worry about electrocuting myself or burning anything. Oh, but then that's not really working, is it? Maybe I can put it, I'll put it like that. That's a half measure. And then I'm going to bring my apparently badly wired breadboard back into shot. Oh, running over cables, don't like to do that. Right, okay, good. Now I've sat down again, I need some more patch cables. Oh, still some for here. So, right, we need to take a square wave. So I've got a pulse wave here, right? Coming from this thing here, the Erica Synths black modulator. I'm going to use that. It might not be the right thing. Shouldn't we really be looking at this on a scope? Oh my goodness, we've just not got this going right at all. So anyway, this is going to go into the input here. Then we're going to need to take the output to control the filter. I think that was the plan. So output into the FM input, or yeah, the FM input on the filter. That's what we're after, yeah? Can you hear that all right? Can you hear something? I don't think I've got it plumbed through entirely. And then, hopefully, what we should do is turn up the resistor, and that should give us the slope that we're looking for. That is not what I expected. That's not what I expected at all. Right. Alright, so okay, so this is the reason why this isn't working, is because I have it backwards, right? I have it backwards, so let's unplug this and unplug this. So it says you need the LFO to go in the right hand socket. See, I'm just assuming it's left to right for no reason, but that's, you know, that's evidently my assumption. So it's the right hand one that puts the LFO, and the output is on the left hand side. Hopefully that will provide a different result. Yes, are you hearing that? Yeah, it does sound like an old episode of Doctor Who. Yes, I'm expecting the soup dragon at any time. Okay, cool. Now I could potentially have a look at this on my Magic Chinese scope, because I do happen to have that knocking around here. Look. So why don't I attempt that in a I know something about electronics kind of way. I seem to have turned that off. That is here. Okay. Oh, I've broken it or eaten it or something. Oh no, we need to turn it on there. There we go. So theoretically, if I take, so the output is the green one, no, is the black one. So if I take that, see, the problem now is that's going to have to require me to fiddle with things like I know what I'm doing in order to get this to be measurable of something. Hang on. Okay, DC. What's that changing? Okay. It's not far off. Damn it. How do I need to do this? I need that one, don't I? Alright, can you see that? That's some kind of square wave, that is. So that's the pulse coming through, with a bit of luck, if I don't mess it about. Oh, I've lost it. It was there, it was there, you saw it. There, it's back. No, it's not. Is it to do with this bit here? Is it because I'm shorting out something? Oh, it was working, it was there. Which bit is not working now? Am I shorting it out on the back? Oh, it was definitely... There it is again. Oh, that's peculiar. Alright, it's there. I have no clue. Now, okay, I've got it. I'm going to turn the knob, turning the knob, turning the knob. Look, 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 the envelope is revealed. Look at that. And back again. Yeah, good. I think I completely aced that. Awesome, awesome. Right, good. I don't know. I need to look at that again. I need, I need to spend time with some things. Let's put that over there. Wait, right, good. So we aced that extraordinarily. So the only problem with this, apparently, this is not a done deal yet, is that the attack and release phases are not adjustable independently. No, that's true. So changing one will also change the other. Yes, that's what's happening in what we're seeing here. Oh look, they did a circuit simulator thing where you can follow the link and it will show you it. Should we try that? Okay, this might be helpful. Let's just go to this. Good, you can see that all right. So this is the simplest envelope that we've just done, and we demonstrated this brilliantly on our scope. I can't quite believe how awesomely that went. And you can see by this animated version here, which is, these are fantastic, these things, absolutely fantastic. It shows you exactly what's going on as it happens. The filling up of the capacitor and the emptying of it again. Now we're going to, and then we've got the, that's what's happening going into there, and there's the variable resistance version, which is the one that we use, which are able to change the whole thing going on. That's a brilliant representation of what's happening. I've almost grasped this whole capacitor to ground thing. Almost, I won't say that I have, but it's becoming familiar and it's becoming hopefully a happy place. Good. Oh. Right, where were we? Oh, it's going to get complicated. So, from there, how can we separate the two, it says? Well, it's actually really easy. Great. All we need is 2 diodes and another pot. Awesome. So we have a square wave coming in. We've got this array of diodes going one way and coming back the other, with 2 pots, and we've got our capacitor to ground again, and that is going to give us the ability to, because the whole thing with the capacitor, it fills up, and going in that direction, that does things to the rise of that waveform, and then as it empties back the other way, so it's going to come around the bottom side through this other diode, because it can only travel in one direction, that's going to affect the fall. So that's how we get our AR envelope. But let's read to make sure I got that right. So the diodes are basically one-way streets for electricity. So by putting two of them in parallel facing opposite directions, we are taking a two-way street and splitting it into two one-way streets. Excellent. Where before our capacitor was charged and discharged through the same resistor, now each phase gets their own resistor. So when the input swings high, a current will flow through the top and through the top potentiometer and into the capacitor. During the low phase, it will go the other path. This means that the one potentiometer now controls the attack and the other one controls the release. Phenomenal. Let's do that then. So here's our picture. It's changed a bit. It's almost completely changed. Right, so I'm just going to turn this off and focus on the breadboard again. So this, where am I going to put this for the minute? I don't know. I could take the power out. Yeah, take the power out, put it over there. Just put this over here for a minute. Okay, good. You still with me? Good, good, good. Right, breadboard in place. I think we might have to start from scratch with all of this. Come on, be nice. Let's just take out one of the power things, just so I've not got power going through it for the minute. Stay out of the way, thank you. Right, so over here it's got a cable going from ground, which is the top, over there, and then it's got a pot that's ground on that leg, like so. And then we're taking this bottom leg and just moving it over for reasons I can't explain. Don't suppose it matters, we're just putting it over a couple. Good. Then we've got, wonder which diodes we're using. Are we using the stocky ones? Or are we using the little ones? Doesn't say. Does it matter? I mean, these are a bit chunky. If I go back, right, I'm just going to try to think about this for 1 second. If I go back to the original circuit, there's a thing there that we're trying to do. How do I know which diodes they are? So I go to the circuit diagram at the end, perhaps. So it's the 1N4148s that it's using in that part of the diagram. Go back up to the bill of materials. Process of elimination is what it's all about. Diodes, some diodes. There's 6 of those. Right. So it was the 1N4148s that were used in that particular circuit, which is exactly what we're doing. So it's going to be the little ones we're going to use, these two. That's my plan. The little ones. There you go. Rumble Flumply Flump on there says use the little ones. Thank you. I will do so. But do you like the way I worked that out? I thought that was impressive. I thought that was mature engineering-y kind of thing. Except now I've lost my place. I don't know where I am. So down here somewhere. Oh, an AR. We're never going to get through this, are we? Easy, I said it's going to be, this one. And yet here we are. Active. There's a lot more envelopes to get through. Here we are. Passive AR envelope. Good. Right. So, alongside that cable that I put in, I need to do a bit of dioding, and the line, which is the black line on the front there, goes with the line on the diagram right next to that, and it goes over, he's just going over three sockets, so it should just go in like that. Beautiful. Got another cable which goes from this one to the middle leg of the pot. So there's one of these 1 meg pots. You can put that in. Now the first leg needs to line up with the other side of the diode, so I can put that in there. And this needs to line up with the middle one, which is there. Good. Another middle one goes over here to the capacitor. Then the capacitor goes to ground on the other leg. And then we've got some crossing over onto the other side from this leg here next to the diode, but taking the middle leg from the pot, that goes across. And over here the other side of the diode, which I can't get to because I put the diode in the wrong place. I need to put the diode up 1 level, which is fine. Yeah, that's all fine. That's still connected to that, that's still connected to that, and that goes over here. And in between goes the other diode, facing the other way, so the black thing going that way round, going into there. Good. Another cable. It's going to go from that side of the diode over here to the other jack socket somehow. Jack socket, just this way around, goes to the back of the jack socket. Good. Front end of the jack socket also goes to ground. Another pot, 1 meg pot. Goes in over here, and this goes into the front end of the diode on that 1 pin. There. The middle one goes to there, yes it does. This cable here kind of weirdly puts in a little one to put it into the front of, or rather the back of the diode, whereas it could have just plugged straight into it. That's a little bit odd, but anyway, that just goes to connect that to that. That seems to be right. That's to there, that's to there. I've got that cable going to there. Got the 2 diodes, the thing going on, and the what's it. Good, right. That was all easy then. So if you connect the LFO and filter like before, you should be able to sculpt it much more freely. Are we going to hear that? That's the question. Right, so let's put this back over here. I'm going to plug this cable in to that bit there to power the thing. Bringing back in our exciting machine. Needs power. I've got a light. So my LFO, as far as I know, was going into the right, the same as it did before. Well, we'll soon find out, I suppose. That's going to go into there. And then it was... what happened to our other cable? Here. So if I So as you can hear, hopefully, we've already got one side doing differently to the other. So let's turn one of my knobs. So that's now flat on the release. I turn that up. That's now taking longer to go down. So in which case this side should be the attack. No, you can't really see it with my fingers. I'm sorry about that. But this side here should be the attack. Yeah, there you go. So that's the attack. Over here, this is the release. See, that's putting it just back to normal. And then that's increasing it. Brilliant. I don't think I need to demonstrate that on the scope because that was a little bit like too hard. Or shall I just try it anyway because I'm that kind of guy? What is it about this that's shorting then, I wonder? Well, I mean, anything could be shorting because I'm just sticking it on stuff, which is part of my problem. Not that I have a problem, but you know, problems have been known. So this, let's just try it out just in case it works. Just like that. Yeah, there it is. Can you see that all right? That's just genius, that is. So if I turn this down, it should get sharper. There you go. Oh! If I turn this one down, that should also then go back to a full square. There we go. Look at that. Flipping Nora. That is awesome. Well, we are acing this, boys and girls. We are acing this. So turn that off before I blow myself up. Good. Right. So back to the manual then. So why is it passive? Because it doesn't include any form of amplification. Okay. It's getting its power from the square wave. Is that a problem? Well, that much depends on what your goals and context are. In this current form, the envelope can only properly function if two external conditions are met. The circuit triggering it, in our case the LFO, needs to be able to provide enough current, right? And the current we're controlling, in our case the filter, needs to draw as little current as possible from our envelope. Well, let's imagine why. Let's imagine we put a big resistor between our LFO and the envelope. This way we are severely limiting the amount of current flowing. And that means that even if we dial our attack and release pots all the way down, charging and discharging a capacitor will not be instant, as we'd expect, but instead would take a while. See, I've read that and I don't really know what that means. What are we saying? On the other side, imagine our filter. Okay. Let's imagine we put a big resistor, severely limiting the current flow. That means that even if we dial our attack release all the way down, charging, discharging will not be instant. It will take a while. What, because there's a big resistor? I guess it takes longer to go through because it's a smaller opening. On the other side, imagine our filter is also using an envelope to drive than LEDs. LEDs basically dials that light up. They're power hungry. Alright. And it would severely restrict our envelope's range because current is being lost through other things. Okay. A well-designed module should always have high current outputs and low to no current inputs, which, ironically, is a standard our envelope here does not live up to at all. It eats up our oscillator signal while providing barely anything for the filter. Fair enough, okay. That's interesting. I'd never considered that at all. So fixing it is really straightforward. Ray! We'll simply set up an op-amp. Ooh, crikey. Op-amp buffers, both at the in and the output. The buffers measure a voltage and provide an identical copy at their output, while being able to supply a decent amount of current. Because of that, it no longer really matters how much current the input can provide and how much the next circuit eats up. Okay, so we're having some buffering op-amps. Awesome. Oops. There's the circuit. So we've got our gate in, or our signal coming in. Our LFO has been doing that. And it goes into an op-amp, which has some shenanigans, which goes through a diode. then as a grounding resistor through another op amp into our twiddly diode pair, into our, so our envelope bit over here. This is our enveloping bit, and we've got this array of stuff before and this one afterwards. This is just sort of feedback smoothing, isn't it? I seem to remember. Okay. So why do we have a 1k resistor at the output then? Well, this is an additional stuff, and all this additional stuff at the input. That's what I just asked. So what? Well, unfortunately, there are other worst case scenarios we need to consider. The first one being the classic user error. Imagine that a user plugs our envelope's output into some other module's output by accident. If that other module also uses a buffer, we'll create a short circuit. Since buffers can not only source but also sink plenty of current. So by placing a 1k resistor before the output, we make sure, in this scenario, the maximum output of the current flowing is limited. Okay. Whatever. Saving our op amp for potentially, saving it from a potentially early grave. Gotcha. Okay, easy. Now, let's tackle the additional op amp on the left. What kind of problem does this fix? Well, so I can see both things on the screen at once. Come on, behave. Well, while it did make sure our circuit gets, while we did make sure that our circuit gets enough current, we haven't thought about the voltage we're feeding it yet. We should, though, because that voltage will determine the voltage range across which our envelope is operating. Right. If all our envelope does is take the input signal and make the rising and falling less steep, then the maximum height is completely determined by that input signal. That's a problem because if the input signal would, for example, just swing between 0 and 1 volts, that curve would be really small, and a smaller curve means reduced range of effect. When controlling our filter, we'd barely be able to move the cutoff point. So I guess what we're saying is we want to remove the strength of the input gate from the equation so that we can properly dictate what the envelope does. If all our envelope does is take the input signal to make the rise fall less steep, the maximum height will be determined by the signal signal. Yes, that's what we did. Okay. So basically our envelope would behave very differently depending on what kind of circuit we use as the input. What happened there? The circuit we use to drive it. And for me this would get very annoying very fast. But since it's very easy to eliminate this kind of external discrepancy or dependency, we'll get rid of it. To do that we use another op amp which we set up in a comparator configuration. Comparator, if you don't know, we have done this before, basically just looks at the input voltage, compares that input voltage to a reference voltage, and then tells us which one is higher. How does it tell us? By either pushing its output voltage up to the positive or putting it down to the negative supply rail. So in our case, that would be either plus or minus 12 volts. Here's how it works in detail. Okay, heavy stuff. I've set up a voltage divider to get our reference voltage. Right. Okay. Oh, heck. Oh, so we've got 12 volts and we're dividing it with a pair of resistors. 100k, 47k gives us approximately 3.8 volts to work with. So whenever our input voltage is higher than that, the comparator's output will jump to plus 12. And if it drops lower, it goes to minus 12. So why choose that threshold? Mostly just because I had those resistors lying around. But 3.8 volts is a decent value. It's low enough so that any sequencer should be able to trigger the comparator, but definitely high enough to prevent it from firing randomly because of interference. Right, so you're setting a threshold above which the gate has to reach in order to make the thing happen. Gotcha. So now our envelope will always get the same 12 volts to work with as long as our input signal passes the 3.8 threshold. Great, because otherwise, so the op amp is comparing whatever it is that's coming in. So it doesn't matter how tall that that square wave is coming in, that gate coming in, just as long as it's high enough to get above the 3.8 volts. I mean, commonly you'll have a gate signal of at least 5 volts, if not 10 volts, then in Eurorack, then that is going to work. And anything that drops below that, even if it's a little bit wobbly, is not going to trigger that gate. Sorted. Sorted. And now the envelope will be able to move over an entire 12 volts, which is just awesome. So this is not, okay, so once the input drops, it will swing down to minus 12. This is not ideal, because the baseline for an envelope is supposed to be 0. Yeah, that's right. You don't actually want a negative envelope, you want it to close. You don't want it to then open as an inverted something or other. You want it just to go to 0. Which is why we put a diode followed by a 100k resistor to ground between our comparator's output and the buffer's input. See, we got that? Okay, got that there. So here's our input. This is our comparator. It goes to 12 volts, goes storming through here to here. When it's not above 3.8, it goes to minus 12, which also goes through here. So whenever the comparator is pushing out 12 volts, the diode conducts, and we also get 12 volts at the buffer's input here. The buffer's input would be undefined, okay? But since we have a 100k resistor going to ground here, that input gets pulled down to 0 instead. So normally it would be undefined, the input, okay, or floating, right? But we've got this here, and so it gets pulled down to 0 instead. Okay. Okay. So when it's talking about plus and minus 12 volts, there's a note here. We are actually talking about plus and minus 9 because we're using those batteries as opposed to a steady supply. It's just a thought, so you don't get confused by that. So with this, we've now forced the envelope's operating voltage range to always be between 0 and 12. See, I don't fully understand. I know what it's saying. So when 12 goes through here, it just goes through the thing. When minus 12, apparently it stays at 0, because this, when nothing's going on, this goes to 0 because it's all being pulled to ground, I think. So why would that, when it's minus 12, why is that the same? I don't know. I guess minus 12 is trying to pull stuff back so it can't. Would that be right? I don't know. So I don't quite grasp that, but that's okay. I'm just going to try to go with it. So to see if it works. Right, good. We like seeing if it works. Let's try it on the breadboard. Make sure that the two chips are set up exactly. If you reverse the power, they'll heat up and die. Right, excellent. So this is what we're trying to do. I'm going to move this out of the way again for the moment. Minus 12 is blocked by the diode. Okay, so that was right then. Minus 12 is moving in the opposite direction. Cool. All right, good. See, I am learning. I am learning, I promise. This isn't all just a complete and utter waste of time. Now, how much has that changed? Has that changed a lot? Yeah. Am I going to have to start this from scratch? No. I've got a resistor, a 1K. Yeah, probably. It might be better if I do a little bit. But let's take the power out to start with. Just to stop it flowing in either direction. So this is the same. This can come out here. And this is staying there. Let me get rid of that cable for the minute. Right, so this is right. Do you want this zoomed in a little bit? Would that be helpful? Put this forward. Might have to use my glasses. Where are my glasses? Here. I'm just going to move this out. So I'm going to move this closer to myself. So, we need a 1K. 1K, here's a 1K. This fella here, 1K. Right, this is going to take a little bit of focus, I think. I'm going to pull out most of these because they're just, I need to do as methodical as I can with this. So that's going to there. I'm going to move this up one so it's more in line with what's on the picture. I've got this more or less in the right place. I need my 1K resistor to go between this bottom leg and there. That then goes next to that diode in the right direction, with its third leg going to the pot as it was before, so that's good. Okay, so let's continue along the top for the moment. So I want something next to that resistor, which goes a long way, and I'm not going to even plug in yet. And on the other side of the diode, which goes to the middle pin on the pot, that goes into the first leg of our capacitor, which is still here. That's good. So this other leg goes one past the capacitor. One. Which line are we on? This one. One past the capacitor. Into there. Now, one of our things here, are they all the same? Yep. Just going to use my magic tool. Make sure those legs are nicely straight. Now I've got to use the little mark on here that's on the manual, and this does not go onto this wire, it goes on the next one across, so it goes there, that way up like that. So that wire is not connected to it. What wire is that connected to? Connected to another one which goes to there. See, that's interesting. Why doesn't it just go straight to it? Sure, that's, I don't know. Maybe it's to do with the length of patch wires that Moritz had when he was putting it together. Who knows? But it's going to follow it as precisely as we can. So, the other leg from the capacitor has to go to ground. So that is, 2, 3, this one. That goes to ground over there. Got that one in. We need the end of this green wire that's come all the way over from that resistor. It's going to go into the second pin along, 1, 2, on the op amp, like so. Now the first pin there, I don't know that it's pin 1. I can't quite remember. I'm not interested. I'm just trying to describe it. So this first pin on the top right, or if you're looking at it from that way, this one over here, that's top left, I don't know, whatever, this one up here, right, that one, follow that along, goes there, and that is going into the positive voltage. That's the positive voltage. Good. That's in there into the second one. Okay, the second one also gets a mini cable to connect it up to the input of the next one. Right. So pin, that second pin goes up to the next op amp presumably, or is it the feedback one? Oh no, I don't know. I'm not going to think about it too hard just yet. Okay, good. Now we have another cable that comes from this fourth pin, and that goes back to the first leg of the capacitor. So where that orange cable is. Good. I've got a slightly dodgy cable there. I'm going to replace that with something else. So what was that from? That was from cable number 2. Point number 2 going back to that green cable. Good. Got the little one up there doing nothing. Got that going back over to the capacitor. That's good. Right, that little section is good. Then heading over here, I've got the front edge of that diode coming all the way across. I've got a little pin connecting that to the back of this diode. Like so. I've got another cable going across from this orange cable, which is next to the diode, coming to the middle pin on that pot. And then I've got a long cable going from the back end, what's going on there, back end of that diode, all the way over to this other pin on this side of our op amp. Good. Oh, that's a super long loony one. Right. That then ties itself into the second pin. I've got my 100K. This is the sink going to ground. That comes off that third pin right at the bottom, third pin. And ground is the middle one where all these other connections are. Good. I have another one from that third pin. Going over here somewhere, I'm not going to worry about for the moment. And I've got the last pin, pin 4 on that side, going to negative. Okay. Good. That's all that section, I believe. I've now got this crazy thing coming all the way over here, just past 40 to there. That has another diode. I'm going to assume it's the same type of diode, because the big fat diodes I think are to do with the power supply, so those can be treated differently, whereas the little ones are to do with the operation of stuff. So this one is that way round, and this comes off the end of this and goes up to about 45, like that. Okay. So I need a second chip. Same orientation, same way up. This has got one pin that goes to that diode, so it goes in like so on the 45 line. Yes. Good. Right. Another cable. Goes from one in from that, so not connected to the diode, into pin 2 on this side. That then takes another 100k resistor, hops over the gap there, hops over the gap and ultimately goes to the positive. Plugs in there, into the positive side. Cool. That goes into number 2. That is going into number 1. I need a 47k. 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 I'm going to have to measure all these when I take them back out again, so I know which is which. Got 47k comes off. The second goes to ground. 47k comes off the second, goes to ground. Okay, I've got a cable, comes off a third pin, goes out to the jack over here. I'll do that in a second. I've got another one going to positive from pin 1 on this side. 100k, that 47k. There should be a cable going from pin 4 on this side to negative. Got that going out. That there, that there, that across, that there. That's good. Use my socket backwards into there. Take that end into ground. That should be it. That should be the business. What have we tried to achieve? It was, oh yeah, we're trying to achieve a comparator. So we're not having to rely on the input gate, that's always going to be at the right level to produce the best range of envelope. That's the key. Now go ahead and test it. The range of filter movement should be significantly increased. Alright, super. So let's think about how these went in. So I've got negative voltage going in the bottom there, positive voltage going on the inner side there. That should turn it all on. Let's bring this back out. Bring in a little bit of modular. So the output of our LFO is going in there. Input to the filter is coming from here. And we should get a greater range. Let's hope we can hear that, eh? Power, 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 power. Power, power, power. Yeah, quite possibly. Let's turn this up. Turn this up. Lovely, great stuff. Enveloping things we are. Right, now we have to look at other alternative bits of envelopes. Let's have a look, see where we get to. So, yeah. back to the manual. AR versus ASR envelopes. Sorry, AR versus ADSR. Right. Well, we could leave it there. I'd rather put in a bit more effort in order to give us a finer control of the envelope's curve shape. On the left side here, I've drawn up what the current circuit is capable of producing. Sort of attack, and then holds it, and then releases. But we want an ADSR or something approximating that. Okay. So this is more complex attack, decay, sustain, release curve. What's the difference? Well, both curves have an attack and release, but the one on the right adds a decay phase and the ability to set a specific sustain level. The idea is that if the sustain is set to a lower level than the peak, then we can drop after the attack, and this is the decay phase. But once that's through, the curve settles on a set level while the input stays high, and from here we enter the release phase once the input swings low. Benefit of the added complexity, we can produce a wider variety of sounds. Personally, I like the short plucky percussive hits and also the gliding acid bass lines. Both of them are not really doable with a simple attack release envelope. Are they not? Now, turning the circuit we have into a proper ADSR is somewhat out of the scope of this project. Interesting. Still, with very little effort, we can build something that approximates it. Okay, I like shortcuts. The pseudo ADSR envelope. Here we go. So here's how that would work. As you can see, yeah, right. I've basically copied our comparator and pasted it down the bottom. So I use a mouse so you can see what I'm pointing at. This thing here and this thing here, I think. Yeah, why not? Let's just say that it is. Both the new and the original one get the input signal and they share the same reference voltage, right? Which is this made by the comparator in the middle. That's the reference voltage. I've placed a high pass filter before the top one. Oh, this thing here, a diode and a 10k what's it with a thingy flob. Good. The high pass would normally turn a square wave into two short voltage spikes, right? First a positive one when the input transitions from low to high, and then a negative one when it drops from high to low. Now, since we're not interested in the negative spike, and it could cause our comparator to glitch, I've decided to eliminate it using another diode. So whenever the voltage at the comparator's input goes negative, the diode will open and therefore neutralize it. Okay, so with this, what I'm understanding by the diode things and the flowing of current is that if you get a negative, then current is flowing in the opposite direction, and rather than coming out of the comparator, which is over here, it comes straight out of the ground, because that's the easiest direction of flow, I suppose. Okay. Okay, but what do we need for the positive spike for? Simple. Well, feeding this positive spike into our comparator, we get a quick 12-volt burst right when the envelope is triggered. So with a fast attack, the envelope's curve will always start at the peak level. Alright. Right. Why is that important? Okay, we'll first have to talk about the other comparator. Since this doesn't have a high pass at its input, it will simply behave like the comparator in the previous iteration. Whenever the input voltage is above 3.8, we get a constant 12 volts at the output. The diode afterwards serves the same purpose as one at the top, to block the low state. Okay, after this, I've set up another potentiometer at a variable voltage divider. This allows us to take the 12 volts during the comparator's high phase and freely scale them to any value between 12 and 0. Whatever voltage we dial in here will be our sustain level, because the 100k resistor at the input buffer doesn't connect straight to ground like before, but rather to our sustain level voltage. That sounds confusing. Let's break it down. Okay, got to break it down. Our input starts out low. This means that both our comparator's outputs sit at minus 12. Right. Because of the two diodes, this doesn't propagate. So our buffer's input gets pulled down to 0 through the 100k resistor. Okay. And potentiometer, giving us 0 volts at the envelope's output as well. So let's just talk about this. So if it's got a negative, it always ends up with 0, because anything that tries to pull back can't go through the diode and instead just goes straight through this to ground. So the input goes high. This will do two things. We get a voltage spike at the top op amp, which gives us a 12 volt output here quickly. At the same time, the other one, the one at the bottom, pushes out a constant 12 that gets scaled down by our sustained potentiometer. So this pot here so we get 12 volts here. What's going on with my mouse today? So we get 12 volts here, and down here, a 12 volt burst at the top, and down here we get something set by this pot, which is becoming our sustain level. Okay. Let's assume we've set it to about 50%. This means that at the buffer's input, we've got our 12 volt burst coming from the top and a constant 6 volts coming from the bottom. Since there's no resistor in the top path, but 100k in the bottom one, the burst will win and push the overall voltage at the buffer's input up to about 12. Our buffer, being a buffer, will copy those 12 volts and push them through the attack potentiometer. Again, we're assuming we've dialed in a fast attack. There will be plenty of low resistance in its path, allowing the capacitor to be charged up to about 12 volts before the burst is over. So at this point, our envelope's output sits somewhere between 12 volts, its peak value. But because the burst is just a burst, it will quickly die, and the top comparator's output will drop to minus 12. So suddenly, with the top diode blocking, the only voltage applied to the input is our sustain level at 6. Okay. So the 12 volts overrides the 6, but then because the 12 volts is a burst, it disappears quickly, which means the 6 volts then takes over. This means that our buffer's output will drop from 12 to 6, allowing our capacitor to partially discharge through the release path. But remember, the burst charged it up to around 12. Yeah, okay, yeah. Once the voltage of the capacitor has dropped to the sustain level, it will stabilise, giving us a constant 6. Up until the input signal swings low, our buffer's output Until the input signal swings low, our buffer's output drops to 0 and the capacitor is allowed to complete the discharge process. The result is an output curve with 4 distinct phases: an attack, then decay, which is coming down to that 6, then the 6, and then the release. There are two rather big caveats here. First, both in the decay and the release phase, the capacitor discharges through the same potentiometer. Yeah, because that's affecting the same capacitor. The capacitor has charged up, it releases a bit to get to the sustain level, and then it releases more to get to the release, to get back to 0. This means that you can't control those two phases individually. Changing one will also change the other. So we can never have a curve with a long decay and a super short release. Alright. We're essentially giving it a two-stage release, I suppose, is the way we're thinking about it. Second, the decay phase is directly dependent. The decay phase is directly dependent on the set attack. If we dial in a slow attack, the capacitor will not be charged up to the peak level during the initial short burst. Maybe it won't even reach the sustain level, let alone surpass it. So in effect, we basically skip the decay phase as we are never dropping down to the sustain level. A proper ADSR shouldn't have these two problems. But for how simple our circuit is and how few components it uses, I think we can book this as a worthwhile trade-off. That's a strange expression. So let's set this up on the breadboard. Hurrah! Okay, I think this is almost like the final bit, which is quite exciting, considering it's 9:30. Oh, that's this LED we've got to do. And then there's more things to think about. Oh, there's a fair bit. Oh, there's looping. Crikey. All right, there's quite a bit to think about yet. But let's see how far we get with what we're doing, which I think this is the important bit. Right, so this uses another bunch of op amps. Shit, right. Stuff to do. So although, I mean, it's interesting how this is a simple circuit and it's a simple idea and it's a simplified version of an envelope. But the detail we've been able to go into has been really quite interesting, and I've enjoyed the stages of changing one thing which smoothed out a square wave, and then now changing two things which are doing that. Now using the op amps in order to control the voltage coming in, and now we're going to introduce this sort of sustain stage, which is really interesting. And it may be that we just get to that point and that might well be enough. But we'll see. Because we don't, it's 9:30, that's 2 hours. That's quite a long time. So I wouldn't like to go much past 10 if I can help it. That's the plan, all right, everybody? So back to our breadboard. Let's see whether we can sort this out. Good. Right, let's take that out. How much of this can we keep from last time? That's the question. It'd be nice if that was highlighted, wasn't it? I'm going to take out my battery for the moment, so I don't accidentally hurt myself. Not hurt myself, hurt a component. And I might need my glasses. Or maybe not. So, what has changed? We're putting in a sustain stage. Cheers, Andy. Thanks for sticking with us. Otherwise, is that all the same? That first one, that's the 100k. So he's given us enough space to fit this other bit in the middle, I think. Yeah, I think so. We're just going to take out this third one, rather than going all the way over to there. It's now going... Oh, it is still going all the way over to there. It's just like tag teaming its way. That's quite funny. Why not just have a long one? Maybe that gets... Why would that get confusing? I don't know. Anyway, Let's see if we can follow exactly. So this yellow cable here, which was going all the way over to this 100k, that is now pulling back and is going to just 2 out from here. 1, 2, so there. And this should be on the second row of things apparently. So let's try to get it exactly right, as your man says. So that's there. Now at the end of this, there's another cable. It's going to get crowded. And there's a 100k resistor. And that's just going to go across a skip 1 to there. Now we need another pot. Now I've already got 2 pots involved, so this must be our other pot. Can't be anything else. Must be our 100k. Yes, it is 100k, isn't it? Of course, we had that on the flipping diagram. So this needs to go in here. So it's the first leg is not on the same one as the resistor. It's the middle one that needs to be on that second one. It's on that other leg. So it goes in there. Good. Good. Get access to that. That'll be a blooming miracle. Now this green one, which starts off by not being on a leg on this side, goes all the way across to not being on a leg on the other side. Are you following me? So it goes past the pot. And there's a cable that goes from pin 1 in between the resistor, onto ground. Okie doke. Now there's another diode. It's black line going that way. Black line going that way. That goes on to pin 3. And it just misses 1 to go to there. And that is also the first pin on this chip. Same orientation. And it needs to go. I don't know that I've got enough room. I might have to do some shifting. I think I might have to. It should go. Yeah, so that's not right, is it? That all needs to move across a bit. No, I'm trying to go in here. So I've got 4. I will fit in there. I've just got to move my 100k along a little bit. I move my 100k. And needs a little bit more room. So 100k up to there. This cable goes with it. 100k. Over on this side, this goes with it. There. So up to the 100k this way round. This fella goes in here. Okay. Near as damn it. Okay, I've got a diode down here. Now this diode, that diode should be going from there to pin 1, which it is. This diode needs to be going from not pin 4. It must be going from pin 4, otherwise it's not connected to anything. Pin 1. No, it's going to be connected to that, which is coming over there. Oh, this is tricky. So that does not want to be connected to pin 4. It needs to be connected to there. I'll just pull that out. Alright, just a minute. It's going to get tricky. There's my 100k. I need space between that and the next one. So I think I'm going to have to move everything down a bit. So is that no longer on 45? It is on 45. So how am I not fitting this in? Where have I gone a little bit fat with this whole thing here? So I think this needs to move across a little bit. Move the camera a bit to the right. I don't quite know what you mean. Do you mean this that way? Or do you mean I need to move to the left? Like that? So you can see more of the breadboard? Okay, cool. Right. Focus. This is important. So I've got that in there is going to pin 1. I've got this green cable here going in between. I need a cable to go from in between that. Think about where I am. To the other side of the op amp. In between that to the other side of the op amp. Like that. That, I believe, connects to this other diode, which goes to pin 1 on there. Now I need another 100k. Did I do that? I did 100k there. No, that's fine. That's where that is. That's to that. That's to that. That's going to pin 1, which it is. Anything else going to that? No. On the other side, let's not forget, I need that pin 1 to go to positive. Right. Pin 2 It's going to go to the 100k. So pin 2. Pin 2 goes to the 100k over here. Where is that leg? Is that leg with that one? Which is going to there. Yes. It's not with that yellow one, it's with that one there. It goes to the 100k. It doesn't go to the diode. That's right. Good. Then I've got another cable. It goes from pin 3. And that goes past 100k in between, but not to the other op amp. That's pin 3. That's not pin 3. That's pin 3. That is then really that is going to this bit here. I mustn't forget that this end is the input. I am confused by going that way round, I have to say, but we can't help that. So that was coming out of there. Now this is coming out of that one. Right. So this has to go to pin 3. Pin 3 has been brought to there, so that goes there, which is not connected to that one. It's connected to pin 3. There's a lot of sort of jumping of jumpers. So this cable jumps over to there to connect to another one to jump over to there, when you could just have one cable, and that seems to me to be a simpler way of looking at this. But this is how Moritz does it, so, I just have to keep at it. I just sometimes feel I'm using double the cables, but just go with it, because it's, he knows what he's doing, whereas I do not. I do not. So, 4th one on here needs to go to negative. Alright, we are nearly there, I think. I've got my 100k, which goes over there. I've got stuff going on here. I need to worry about this end now. So I've got the 100k, yep. Going to pin 2, yeah, got that. Anything going to pin 1? Yes, that diode is going to pin 1, and it is. I've then got a 47k resistor. Oh, which I already have there. Yeah, that's going to pin 2. Did I move that? Pin 2 to there. Yeah, to ground. Yeah. And I've got another bloody diode. Oh, heck, I've got a whole other capacitor to put in here yet. Core flip. Yeah, as I say, this whole circuit feels back to front, because this is the input, that's the output. So I've worked it from the out backwards. So now I'm experiencing this high pass filter at the input. That's what I'm coming up against now. That makes sense. So this has got to be this way around. Next to the 47k, going to pin 3. Pin 3 next to the 47k. In between those two, and where's it going to? It's going to ground. That way up? Yes. So I need my other film, I think. And this squeezes somehow between that and that. So that's suggesting that this goes up one. Let's put that up one. Like that. Let's move that down one. Let's take it on that. This cable here can then go up one. Gives me a bit more room to stick this in, which goes there. That should be on that same signal pin on the input, and the back end of it goes to currently nothing. Yep. Which then gets tagged into pin 2, which is what that diode's on. Not pin 2, pin 3, which is what that diode's on. Yes, okay. Are we all holding this together? Are we holding it together? So, same as the diode, pin 3. Yeah. This is complicated. 10K. 10K. That's a 10K. Look at that. 10K, this nice blue one. This is going all the way from the ground leg to pin 2. So the same as I've just put in that other one. It's ridiculous. Into there, same as that diode that comes over. It goes in here. Okay, and we've got that going to a thing. Now, is there any other mystery things I haven't put in? That's in. That's going to negative. Ground, ground. That's a thing that's shorting against that thing. Let's not make that happen. That goes to there. That. I've got 1 to 2. 1 to 2. I don't seem to. Oh, I do have a thing going there. That's coming from pin 4. Is that right? Yeah. Well, I mean, geez, heck. I think that's right. I mean, I think it is. Yeah, Rumple Bumfluff says that that Moritz only uses pre-made wires, which is why they're of only 3 sizes or whatever, which makes the board that little bit busier than perhaps it needs to be. But hey, you know, in the future I'll do my own version of this with my own designs of circuits once I've understood all the circuit designs, and I'll do it simpler or something. I don't know. Anyway, whew, right, so we think we got there. So in here is this sustain knob. How are we going to be? We're just going to have to try it off and see whether it works. So let's come back out. Put this over here. Plug in our negative over here and our positive over here. Bit of luck. Bring in the little modular. So the output of my pulse generator, my LFO, is going into the input, which is on this side. Then the output here is going into my filter. I need power again. What happened to that? Over here somewhere. So with a bit of luck, changing this middle pot should have an effect. So with a longer attack, it sort of goes up to that sustain level. Doesn't quite reach that 6 volts before it starts coming down again. So that's a short attack, which gets the full sustain level. That's no sustain, coming all the way down. That's a lot of sustain. Hey Arthur, good to see you. My middle kid's called Arthur, it's a fantastic name. You're very welcome. So yeah, it's definitely doing a thing. See, this might be really interesting to look at on the scope. So why don't I do that? Let's see if I can get that to work again. So if I then attempt to change sustain again, that's a nice smooth lack of sustain. Add the sustain in and it sticks that bump in. Can you see it? It flattens out before it then releases. If I turn this one down, or is that up? I don't remember. Let's try it the other way. Okay. So there you can see you've got your instant burst followed by a sustain level. And then the release, because I've set them all to very small amounts. If I add a little bit of attack, we should see that, possibly. Oh, I don't know. It sounded like I knew what I was talking about there for a minute. Well, there's definitely an attack thing going on. If I change the sustain. Oh, I don't know. I've broken it. But I think we got the idea there for a minute. Let's take that out. But you could definitely hear something going on that was different to how it was before, which I think is the point we were going for, if nothing else. So, great. It would be nice if we had some visual indication of our voltage. Well, right. Well, I've been doing that, mate. I've been all over it. I've been all over it. But now we're talking about the status LED. What time is it? It's 5 to 10. Let me just have a quick skim through. Is this going to produce a lot of problems or is this going to be easy? Doesn't look too hard. It looks like status LED is quite a simple thing to add without having to mess anything else up. So maybe we'll do that quickly. So I'm going to turn this back on. Do I want to do that? Oh no, okay, not just now. Alright, so let's see if we can add this status LED. Let's just take power out for a minute. Try to keep all this in here as much as possible. So this is to do with something over here. We are going to add our transistor, 3-pin thing here. I'm going to add this out the front here somewhere. I've got with some new cables. That's not connected to that front pin, and it does need 3 of its own sockets. That way up. Oops. Like that. It needs a long wire coming from the back end of this 1K into the middle pin. You've got that pin going to, first pin going to positive, first pin going to positive, we need a 470, which is this fella. That's going from the other pin to the LED. Other pin. And I think that's all we need. So the LED, as far as I can tell, on the manual, it seems as if the flat bit goes over there. So the flat bit, status LED, is there. So the flat bit is pointing at ground, because the flat bit, flat bit is pointing at ground. Flat bit on this, I cannot see. So I need my, where did I put my glasses? Over here. Alright, that's the flat side. The flat side going to palm over to the ground, which is the far one, and this coming into there. Right, that should be all that's required, right? So the negative goes into there, positive goes into the second one. And turn this on, put that out of there, that should be going into there. Look at that! I've blown it now. It was working, you saw it working. There we go, we're back again. It's because that burst on the attack is just a little bit too high. Okay, that's a bit more interesting. Nice! Nice, nice, nice! Hey, Holger, thank you. I don't know what that means, but that's lovely. Yeah, it is interesting how changing the attack, I think, really does mess with that sustain level. But it may be more refined in the actual module rather than on the breadboard, if you know what I mean. So So that was cool. So now I want to talk about the inverted output. I can turn this off now, I think. As nice as that is. So we're now back talking about the inverted output. Which is cool. So they're going to add in, I'm not going to go into any more detail now, I'm just going to sort of bring this to a finish. I think we got to the right place. So the other thing that Moritz wanted to add is an inverted output, which essentially takes or steals that -12 that we keep trying to get rid of and takes that somewhere else, I imagine. It's quite easy apparently with another op amp. Because everything is done with op amps. So it's to do with the output curve being simply flipped on its head. And to do that, there's a whole section over here, which is this circuit that we've just created here. Another pair of op amps, a thing, and a which is making that work, which is awesome. But I think that's going to go on for too long, so I'm not going to do that. And then finally, there's the extra thing, which is the looping, which is interesting. You can pretty much turn any regular envelope into a looping envelope by adding this little circuit. So this has an op amp going in the other direction. You just patch it in between the output and the input. Output on the right, input on the left, and the envelope will re-trigger continuously. We're configuring yet another op amp as a Smit trigger inverter. Think of it like a watchdog which constantly monitors the envelope's output voltage. Whenever it drops back to 0, it will re-trigger and then sit back and wait until it's time to strike again. How exciting. Smit trigger inverter has 2 thresholds against which it compares the voltage we apply to the input. 3 resistors at the top set the thresholds. Bottom threshold is set to 0, top one is set to 8. So when the input drops to 0, the op amp's output will jump to 12. Then once the input rises above the 8 volt line, it will drop down to -12. And we've already got a diode and a 100k resistor to block any negative voltages. Yes, we do. But for loop mode, we'll have to circumvent them. This is because we need to make sure our Smit trigger inverter doesn't get stuck, because as we know, it will only change states if the envelope's output rises above 8 volts. If we use our envelope's regular input, the maximum output will depend on the attack and sustain levels. Dialing in a slow attack and a low sustain might cause the voltage curve to peak at less than 8 volts, which is what we saw by increasing the attack. It didn't reach the full potential. We will break the loop by not triggering, and that will break the loop by not triggering the inverter. So the solution is to connect in the inverter's output directly to the input buffer, ideally through a simple switch that lets us toggle it on or not. Cool, so by circumventing the input comparators, the relationship between our Smit trigger inverter state and the envelope's output voltage becomes a lot simpler. Okay, great, so that adds a load more other garbage around the place, somewhere in there I expect. And with that, our envelope is done. Okay. So if we want to make it permanent, I think we do, dig out the panel and the PC kit, heat it up, and get it done. Great. Great, great, great. So just to show that one more time. There we go. Super. Lovely, 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 lovely. Right. Good. I think we will leave it there, if that's all right. I think that's long enough. I think we got far enough with it. Yeah, really interesting. I mean, I know full well that I haven't retained all of the information that we've acquired through building the other modules. I appreciate that. But then there is about a month between each one of these that we do. So I think if you were to have the whole set and take a week and sit down with it, I think you could learn an awful lot and retain all of that. As it is, we're doing stuff and then we're reaffirming it, and we are gathering up some bits. You know, I understand more about op amps and these resistors that pull things to zero, the comparators. You know, all of these things are starting to become familiar. The language I'm starting to understand. It's starting to trigger things in my head. So that's all really, really positive. My prowess with the breadboard is coming on. I'm understanding that. I don't wire the batteries in wrongly. Thank you very much. Those were all completely fine. So, yeah, you know, I kind of explained what it was I was doing and why that is slightly different to what's on there. You don't go by the positive and negative here. You just go on what it is that you've set up. So, super smashing great. There was further we can go with this, and please do so. You know, follow the instructions through, complete the circuit, all on the breadboard. That would be great. But I think we got to a position where we've got the whole thing working, and it was just like the extras that we haven't quite got time to do yet. Be aware that it does seem to be backwards. We've got the input over here and the output over here, which did have me confused, I think, for the first half of this video. You know, not massively confused, but a little bit. And then that dawned on me as to what it was over here that we were doing. So it does get crazy in there. But that's just the nature of it, I'm afraid. It's great getting the light working. Really enjoyed that. And ultimately, we went from having a square wave which we were tweaking to give it curves, into it not mattering what that input was. It just needed to be a gate. Even though we're continuing to use a square wave, that was unimportant. It just needed to be an on and an off. So I could have got a keyboard over here with CV out, use that to demonstrate it, rather than just a pulse like I was. Exactly the same thing, because you're no longer using the height of that square wave. All it needs to be is enough for the gate. The voltage level of that envelope is being defined by the circuit itself, because of all that comparator stuff that's going in. Because the op amp looks at something, sees it as above a threshold, and then does something and outputs voltage. So you're not using the voltage that's coming in, it's generating its own from the circuit. Does that make sense? So that was quite interesting. So I'm seeing how that works. Not that I ever would have thought that the voltage is created by the gate that comes in. That had never occurred to me at all. So it ended up not being that. So what happens now? Well, now tomorrow, same time, 7:30, we'll come back and we'll pull this apart and we'll stick it onto the PCB, solder it together, and get it to work properly within the context of our system, which will hopefully be. I mean, I've got the VCO and the VCA. I mean, we'll leave the filter in here for now. And what I'll do, I think what we'll probably do is introduce a keyboard into the situation to trigger the envelope for the VCA. Maybe that would be a good thing to do. So yeah, I'll get one of those prepped up. Just to let you know, in case you're wondering, the next module will be the sequencer, which will be released at the end of the month. So that will provide us with all the gates and triggers and notes that we need to drive it as a synthesizer. I mean, as somebody said earlier, it's in some ways you need other modules first before you need other modules, but it's difficult to know exactly which order these things should be done in. You know, if we have the sequencer first, that would be great for everything else going forward, but you wouldn't really know what it was doing. It wasn't doing anything interesting. I think starting with the VCO was the most important thing. Then the VCA, oh, I don't know, I guess. But then the envelope, I don't know, or the filter first, or or the signal, it gets tricky to know. So we're just going with it as it is. And I imagine if this is the only modular that you have, then it's going to be a little bit tricky to start with until you've built up enough modules for it to be able to play itself. But if that's the case, then just bear with us and watch what I'm doing and go yay when I go yay, and you'll just have to wait until you have all the relevant bits in order to play your own system. Thanks, Adamski. That's appreciated. I've been wondering what people in the UK do with getting CDs, cells, LDRs, light-dependent resistors. I mean, I've got lots of compact discs. Is that what you're talking about? What are you talking about? Do we have a lack of light-dependent resistors? Or are you talking about the weather? I don't know. Anyway, thanks for that. So thanks for joining me. That's been super. I do appreciate you spending the time. I hope that's been useful to some degree. My power's dropped out of that. Let's plug that back in before it all disappears. So I will see you all being well tomorrow night for the soldering. That'll be fun. In the meantime, I'll see if I can find my outro. Is that my outro? No, that's a blank screen. No, I'm not going to go for that one then. How about that one? No, that's my coming up. That one? Well, this is fascinating, isn't it? No, it's not that one either. That one then. That's the fella. Right, I got that tuned in. Good. So, yeah, thanks. And good. Nothing else to say, I don't think. See you tomorrow. I need to go and get some sleep. And in the meantime, go make some tunes. You're welcome. Very welcome, everybody. Very welcome.